The morning of April 17, 1944, Rabaul, New Britain. Lieutenant Saburo Sakai adjusted his goggles inside the cramped cockpit of his Mitsubishi A6M Zero fighter, feeling the familiar vibration of the Nakajima Sakai engine beneath him. 1,020 horsepower. 14 cylinders arranged in 2 staggered rows. The same engine that had carried him through 2 years of combat over China, the Philippines, and now the crumbling defensive perimeter around the Solomon Islands. He knew its sound intimately, its particular throaty rumble at full power, the way it coughed when climbing past 18,000 feet in the thin air. Below him, ground crews pushed another Zero into position. Sakai watched them work, noting their efficiency despite shortages that left many aircraft grounded for lack of parts. The mechanics understood these engines. They knew how to coax maximum performance from the radial design, how to time the magnetos precisely, when to adjust the mixture for altitude. These were good engines, reliable engines, engines that had given Japanese naval aviation dominance across the Pacific in 1941 and 1942. What Sakai did not know, what no Japanese pilot at Rabaul knew that morning, was that the American fighters climbing toward them from Guadalcanal were powered by something fundamentally different, something that rendered every assumption about engine performance obsolete. The chance-vought F4U Corsairs, approaching through the morning haze, carried Pratt and Whitney R-2800 double Wasp engines. 18 cylinders, 2,000 horsepower in early production models, 2,300 horsepower with water injection in later variants, more than double the power available to Sakai's Zero. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Japanese simply never knew. Not accurately. Not with the precision that would have allowed them to understand what they faced. Intelligence reports mentioned new American fighters. Captured documents described improved performance. Pilots who survived encounters reported greater speed, better climb rates, devastating firepower. But the specific numbers, the engineering reality, the brutal mathematics of horsepower ratios, remained hidden behind the fog of war and the limitations of Japanese technical intelligence gathering. This ignorance was not an accident. It was systematic, structural, and ultimately catastrophic. When American forces began their island-hopping campaign across the Pacific in 1943, they encountered Japanese aircraft that appeared formidable in photographs and intelligence summaries. The Zero, in particular, had earned a fearsome reputation during the first year of the war. Fast, maneuverable, armed with 20mm cannons, and capable of extraordinary range, but photographs could not convey engine specifications. Radio intercepts could not decode horsepower ratings. Even captured aircraft sometimes failed to reveal the full picture of American technological superiority. The Japanese system of technical intelligence gathering in 1944 bore little resemblance to Allied operations, where American forces established specialized units like the Allied Translator and Interpreter Section in the Southwest Pacific area, staffed with Nisei linguists and technical experts who could rapidly process captured documents. Japanese intelligence relied heavily on pilot reports, visual observations, and occasional examination of crashed aircraft. The sophistication gap was enormous. Japanese pilots returning from combat encounters described American fighters in subjective terms: fast, powerful, difficult to outmaneuver at high speed. These descriptions were accurate but incomplete. They lacked the engineering precision necessary to understand the fundamental technological disparity. A Japanese pilot might report that a Corsair could outclimb his Zero at high altitude, but this observation could not reveal that the American fighter possessed more than twice his engine's horsepower. The problem was compounded by Japan's industrial isolation. By 1944, American submarine operations had severely restricted Japan's ability to import strategic materials and technical information from its European allies. German aircraft engine technology, which might have provided context for understanding American developments, arrived sporadically, if at all. Japan's own engine development proceeded along different paths, prioritizing lightweight and fuel efficiency over raw power. The Nakajima Sakai engine that powered the Zero represented Japanese engineering philosophy at its finest. 14 cylinders, displacing 27.9 litres, produced 1,020 horsepower for takeoff. The engine was reliable, relatively fuel-efficient, and light enough to allow the Zero exceptional range and maneuverability. But it was fundamentally a different class of power plant than the R-2800. Pratt and Whitney's R-2800 double Wasp displaced 45.9 litres, 64% larger than the Sakai. 18 cylinders arranged in 2 rows generated power that Japanese engineers simply were not matching in production aircraft. The R-2800 was capable of producing 2,000 horsepower reliably, with some variants equipped for water injection pushing beyond 2,300 horsepower for brief periods. This was not incremental improvement. This was a different order of magnitude. Japanese intelligence documents from 1944, preserved in captured records after the war, reveal the extent of the knowledge gap. Identification manuals distributed to fighter pilots contained silhouettes of American aircraft, notes on recognition features, estimates of performance characteristics. But these estimates were often derived from visual observation or pilot testimony rather than technical analysis of captured examples. When American aircraft were captured intact, they provided valuable information about construction techniques, armament, and basic design philosophy. But engine specifications required either direct examination of power plants or access to technical documentation that Japanese forces rarely obtained. The few instances where Japanese forces did capture Corsairs provide illuminating examples of the intelligence limitations. In 1945, late in the war, at least one F4U was recovered by Japanese ground forces after a forced landing. The aircraft was examined, repaired using salvaged parts from other crashed Corsairs, and possibly even test-flown by Japanese pilots. But by this point, the war's outcome was already determined. The knowledge gained came too late to inform strategy or influence aircraft development programs that might have narrowed the performance gap. More critically, even when Japanese engineers did examine captured American aircraft engines, they lacked the industrial capacity to replicate the manufacturing processes that made such power outputs reliable. The R-2800 was a masterpiece of American mass production, manufactured with precision tolerances, high-quality alloys, and sophisticated quality control systems. Each engine required approximately 70,000 individual parts, produced by dozens of contractors across the United States, and assembled with extraordinary precision. Japan's industrial base in 1944 simply could not match this level of manufacturing sophistication, even if the engineering knowledge had been available. The strategic implications of this ignorance extended far beyond individual dogfights. Japanese aircraft development programs in 1943 and 1944 proceeded without accurate understanding of the performance benchmarks they needed to meet. The Nakajima Ki-84 Hayate, introduced in 1944 as Japan's answer to American fighter superiority, was powered by the Nakajima Ha-45 Homare engine. This 18-cylinder radial produced approximately 1,800 horsepower, a substantial improvement over earlier Japanese designs. It was still significantly less than the Corsair's power plant. Even Japan's most advanced late-war fighters could not match the raw power available to American pilots. The Ki-84, widely considered the best Japanese fighter to reach production in significant numbers, had a top speed of approximately 387 miles per hour under ideal conditions. The F4U Corsair, introduced in late 1944, could reach 417 miles per hour. This 70-mile-per-hour difference translated directly into tactical advantages in combat, climb performance, dive speed, and the ability to dictate engagement terms. Japanese pilots understood they were being outperformed. They reported it consistently. They developed tactics to compensate, emphasizing tight-turning combat at low speeds, where the Zero's exceptional maneuverability might offset the Corsair's speed advantage. They tried to avoid diving combat where American fighters could use their superior power to break away from unfavorable engagements. But tactics could not overcome fundamental physics. An 1800 horsepower engine simply could not compete with a 2300 horsepower engine in sustained combat. The psychological burden of this disparity weighed heavily on Japanese pilots, who survived long enough to recognize the pattern. They were not being defeated by superior tactics or better training, though American pilot preparation was indeed excellent. They were being defeated by an industrial and technological system that could produce engines they simply could not match. Every encounter reinforced this reality. Every attempt to climb with a Corsair ended with the American fighter pulling away. Every diving attack left Japanese pilots watching enemy aircraft accelerate beyond reach. The technical specifications of the Pratt & Whitney R-2800 double Wasp engine represented a culmination of American engineering development that began in the late 1930s. When the United States Navy Bureau of Aeronautics issued requirements for a new carrier-based fighter in February 1938, speed was the paramount concern. Every other performance characteristic was subordinated to the need for velocity that could overwhelm enemy fighters. The Bureau selected the R-2800 as the powerplant specifically because it was the most powerful air-cooled radial engine available in American production. The engine measured 52.8 inches in diameter and 54.1 inches in length. It weighed 2,360 pounds dry, without fluids or accessories. 18 cylinders arranged in 2 rows of 9 each displaced 2,804 cubic inches, hence the designation R-2800. Each cylinder displaced as much volume as an entire automobile engine of the era. The reciprocating mass of 18 pistons, connecting rods, and valves created enormous forces that required extraordinary precision in manufacturing and assembly. Pratt & Whitney manufactured these engines at facilities in East Hartford, Connecticut, using production techniques that Japanese industry simply could not replicate. Each cylinder barrel was forged from high-quality steel alloy, then machined to tolerances measured in thousandths of an inch. The crankshaft, a single forged piece weighing over 200 pounds, required specialized heat treatment to achieve the necessary strength without brittleness. Quality control inspectors examined every critical component using methods that detected microscopic flaws before assembly. The R-2800 incorporated a 2-stage supercharger that maintained manifold pressure at high altitudes, allowing the engine to produce substantial power well above 20,000 feet. This supercharger system alone represented technological sophistication beyond most Japanese engine programs. It required precision gearing, intercooling systems to reduce compressed air temperature, and sophisticated controls to prevent detonation under varying atmospheric conditions. Water injection systems, introduced in later production variants, allowed brief periods of emergency power by injecting a water-methanol mixture into the intake system. This cooled the intake charge, prevented detonation, and allowed higher manifold pressures. With water injection engaged, the R-2800 could produce 2,300 horsepower or more for several minutes, enough time to escape danger or close for a decisive attack. Japanese engines had no equivalent system in widespread service. The Hamilton Standard hydromatic propeller matched to this engine measured 13 feet 4 inches in diameter on early F4U models. This enormous propeller, larger than any previously fitted to a fighter aircraft, required the Corsair's distinctive inverted gull wing design to provide ground clearance. The propeller itself was a technological marvel, with 3 constant-speed blades that automatically adjusted pitch to maintain optimal engine RPM under varying flight conditions. The hydraulic pitch control system responded faster than any manual system, ensuring the engine always operated at maximum efficiency. Contrast this with Japanese fighter aircraft of 1944. The Mitsubishi A6M50, the most common variant in service at that time, was powered by the Nakajima Sakai 21 engine. This 14-cylinder radial displaced 27.9 litres, produced 1,130 horsepower, and weighed approximately 1,200 pounds. It was a reliable, well-understood engine that Japanese factories could produce in quantity, despite material shortages and industrial strain. But it was, fundamentally outclassed. Even Japan's most advanced production engine, the Nakajima Ha-45 Homare that powered the Ki-84 Hayate fighter, could not match American power outputs. The Homare displaced 35.8 litres, used 18 cylinders like the R-2800, and incorporated direct fuel injection with water methanol boost. Under ideal conditions with excellent fuel and perfect maintenance, it produced 2,000 horsepower at takeoff. This was competitive with early R-2800 variants, but the Homare was notoriously temperamental. It required constant maintenance, precise adjustment, and high-octane fuel that Japanese refineries struggled to provide in sufficient quantity. By 1944, American factories were producing R-2800 engines in numbers that would have seemed impossible to Japanese planners. Pratt & Whitney's main facility in East Hartford operated 3 shifts daily, 7 days weekly. Additional production came from Ford Motor Company's facility in Michigan, where automotive manufacturing expertise translated into aircraft engine production. The company produced approximately 125,000 R-2800 engines during the war, enough to power multiple aircraft types across all theaters of operation. Japanese engine production in 1944 totaled approximately 28,000 aircraft engines of all types. This included training aircraft engines, bomber engines, and fighter power plants. The disparity was not merely quantitative. American engines were more powerful, more reliable, and produced by manufacturing systems that maintained quality even as production scaled upward. Japanese engines grew progressively less reliable as the war continued, as material quality declined and experienced workers became scarce. The R-2800 powered not only the F4U Corsair but also the Republic P-47 Thunderbolt, the Grumman F-6F Hellcat, and the Northrop P-61 Black Widow night fighter. This commonality of power plants simplified logistics, maintenance, and pilot transition training. A mechanic trained on Corsair engines could service Thunderbolts with minimal additional instruction. Spare parts were interchangeable across aircraft types, reducing supply chain complexity. This standardization was a luxury Japanese forces never enjoyed, with multiple incompatible engine types complicating maintenance and straining limited parts supplies. The moment of understanding came differently for different men, but always it came. For some Japanese pilots, realization arrived during their first combat encounter with Corsairs. For others, it accumulated gradually through repeated engagements, where survival depended increasingly on luck rather than skill. The pattern was consistent. Confident Japanese aviators, trained in aircraft they believed competitive, discovering through bitter experience that they faced opponents with decisive technological advantages. Lieutenant Junior Grade Yasuhiko Kuroe, a 30 Victory ace assigned to evaluate captured American aircraft at the Japanese Army Air Inspection Center at Fusa, experienced this revelation in the spring of 1945. American forces had captured a North American P-51C Mustang nicknamed Evelina after its pilot made a forced landing near Japanese positions in China. The aircraft was quickly transported to Japan for examination. Kuro was ordered to fly it. The Mustang, powered by a Packard-built Rolls-Royce Merlin engine producing approximately 1,400 horsepower, was not even the most powerful American fighter Kuro would evaluate. But sitting in its cockpit, starting the engine, feeling the responsiveness of its controls, he understood something Japanese aviation had been missing. The aircraft felt solid, well built. Every system functioned as designed. The engine started reliably, ran smoothly, and responded predictably to throttle inputs. This was not exceptional by American standards. It was simply normal, manufacturing quality. Kuroe flew the Mustang against captured examples of Japanese fighters, including the Ki-43, Ki-61, and Ki-84. The mock combat exercises revealed uncomfortable truths. The Mustang could outdive every Japanese fighter. It could outrun them in level flight above 15,000 feet. Its controls remained responsive at speeds that would render Japanese aircraft nearly uncontrollable. The gap was not subtle. It was fundamental and obvious to any pilot with combat experience. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. But the true revelation came when Japanese engineers examined the Mustang's construction. American manufacturing quality exceeded anything Japanese industry was producing in 1945. Riveting was precise and consistent. Aluminum panels fitted together with minimal gaps. Wiring harnesses were neatly organized and properly shielded. The attention to manufacturing detail suggested an industrial system operating at capacity with plenty of resources and skilled labor. Japan's factories, by contrast, were struggling with material shortages, inexperienced workers replacing men drafted into military service, and bombing damage that disrupted production schedules. For other Japanese pilots, understanding came through examination of crashed American aircraft. When F4U Corsairs began appearing in significant numbers over Rabaul in early 1943, ground crews occasionally recovered wreckage from aircraft shot down or damaged by anti-aircraft fire. The remains told stories that intelligence reports could not convey. The sheer size of the R-2800 engine, visible in cross-section when wreckage was examined, suggested power far beyond Japanese equivalents. The propeller diameter, the robust construction of engine mounts, the multiple redundant systems, all pointed to aircraft designed with assumptions about available resources that Japanese engineers could not make. Lieutenant Saburo Sakai, one of Japan's highest-scoring aces with 64 confirmed victories, survived the war and later wrote extensively about his combat experiences. In his memoirs, he described the psychological impact of encountering American aircraft that could simply refuse combat on unfavorable terms. The Grumman and the Corsair, he wrote, could dive away from us whenever they wanted. They were faster in level flight. If they didn't want to fight, there was nothing we could do. This was the calculus of technological disparity reduced to its simplest terms. Superior engine power translated directly into tactical dominance. The realization was particularly acute among Japanese pilots who had flown in the early war years and survived to face American aircraft in 1944 and 1945. They remembered when Zero fighters could outmaneuver anything the Allies fielded, when Japanese naval aviation dominated the skies over Southeast Asia and the Pacific. They had experienced air superiority firsthand. The contrast with their situation in the war's final years was psychologically devastating. By mid-1944, experienced Japanese naval aviators were becoming scarce. Training programs struggled to produce replacement pilots with anything approaching adequate preparation. New pilots arriving at frontline squadrons often had fewer than 100 flying hours, sometimes as few as 50. These men were thrown into combat against American pilots who had 3 to 4 times as much training time and flew aircraft with overwhelming performance advantages. The survival rate for newly assigned Japanese pilots was measured in days or weeks. Squadron commanders understood their pilots were being sent to almost certain death. They could see the statistical reality. American fighters were faster, climbed better, dove faster, and could break off combat at will. Japanese pilots could win individual engagements through exceptional skill or favorable circumstances, but they could not overcome the systematic advantage American technology provided. Every mission reduced squadron strength. Every loss of an experienced pilot made the remaining missions more dangerous for survivors. Captain Minoru Genda, one of Japan's most respected naval aviators and a key planner of the Pearl Harbor attack, observed American aircraft operations during the Battle of the Philippine Sea in June 1944. He watched American carrier aircraft launch in massive formations, each aircraft representing industrial capacity Japan could not match. The number of aircraft was staggering. More importantly, they operated with a casual efficiency that suggested unlimited resources. American carriers could lose aircraft to accidents or combat and replace them from reserves. Japanese carriers could not afford such losses. The weight of accumulated evidence became impossible to deny. Japanese pilots who survived through 1944 witnessed the progressive degradation of their own capabilities as American technological superiority manifested in every aspect of air combat. It was not merely that American fighters were individually superior. It was that superiority extended across entire systems: engine power, manufacturing quality, pilot training time, maintenance support, fuel quality, ammunition supply, and replacement aircraft availability. The fuel situation alone demonstrated the disparity. American aircraft operated on 100-octane aviation gasoline, sometimes 115-octane for high-performance engines. This high-octane fuel allowed higher compression ratios and manifold pressures without detonation, directly increasing power output. Japanese refineries struggled to produce even 87-octane fuel in sufficient quantities by 1944. Lower octane fuel forced Japanese engines to operate at reduced power settings to prevent destructive detonation, further increasing the performance gap with American aircraft. Maintenance practices revealed similar disparities. American squadrons operated with comprehensive spare parts inventories, specialized tools, and detailed maintenance manuals. Ground crews could perform engine changes in hours using equipment designed specifically for the task. Japanese squadrons made do with limited parts, improvised tools, and mechanics who often lacked adequate training on newer aircraft types. An engine failure that would ground an American aircraft for a day might ground a Japanese aircraft for weeks, while parts were located and transported through supply chains disrupted by submarine interdiction. The pilot training differential compounded these material disadvantages. By late 1944, American naval aviators received approximately 18 months of training before assignment to combat squadrons. They logged 300 to 400 flying hours, practiced extensive gunnery training, and learned combat tactics from instructors with frontline experience. Japanese training programs had been progressively shortened as pilot losses mounted and fuel became scarce. New pilots often arrived at operational units with barely enough flying time to handle their aircraft safely, let alone engage in combat effectively. Japanese naval aviation had entered the war with approximately 3,500 highly trained pilots, men with years of experience and extensive preparation. By mid-1944, most of these men were dead. The replacements were barely adequate for basic flight operations, much less for combat against well-trained Americans flying superior aircraft. The institutional knowledge that made Japanese naval aviation formidable in 1941 and 1942 had been systematically destroyed through attrition. The Battle of the Philippine Sea in June 1944 demonstrated the complete collapse of Japanese naval aviation effectiveness. In what American pilots called the Great Marianas Turkey Shoot, Japanese carrier aircraft attacked American task forces in 3 major strikes. The results were catastrophic. American fighters, including F-6F Hellcats and F4U Corsairs, destroyed approximately 300 Japanese aircraft over 2 days of combat. American losses totaled approximately 30 aircraft, many to operational causes rather than enemy action. The kill ratio approached 10-1 in America's favor. Japanese pilots who survived these engagements described combat conditions that bordered on hopeless. American fighters appeared in overwhelming numbers. They operated with tactical coordination that suggested excellent command and control. They could engage or disengage at will, using superior speed and climb performance to dictate combat terms. Japanese pilots found themselves unable to reach American bombers through screens of defending fighters, unable to escape pursuing Americans, and unable to inflict significant damage even when they did close to weapon range. The psychological trauma of these encounters affected more than just the surviving pilots. Squadron commanders watching their units destroyed in piecemeal fashion understood they were sending men to death for no strategic purpose. Japanese naval planners reviewing operational reports recognized that carrier aviation, once Japan's premier offensive capability, had become nearly irrelevant. The mathematical reality was inescapable. Japan could not produce enough aircraft, train enough pilots, or supply enough fuel to contest American air superiority. For Japanese pilots ordered to attack American positions at Okinawa in the spring of 1945, survival odds approached zero. American radar detected incoming formations at distances exceeding 50 miles. Combat air patrols vectored by fighter direction, officers intercepted Japanese aircraft before they reached their targets. The few aircraft that penetrated to attack range faced concentrated anti-aircraft fire from ships specifically equipped for defense against air attack. The kamikaze tactics adopted by Japan in the war's final months reflected this hopeless calculus. If pilots could not survive conventional attacks, they might at least inflict damage through suicide. Lieutenant Commander Minoru Genda, reflecting after the war on Japan's defeat in the air, attributed it directly to industrial and technological inferiority. "We could not match American production," he stated in post-war interrogations. "We could not match their pilot training. Most critically, we could not match their aircraft performance. Even our newest fighters were inferior to American aircraft that had been in service for 2 years." This assessment, from one of Japan's most knowledgeable aviation officers, captured the essential reality Japanese pilots had learned through bitter experience. The specific numbers confirmed what individual pilots had experienced in combat. American factories produced approximately 300,000 aircraft during World War II. Japan produced approximately 76,000. American production included over 12,000 F4U Corsairs, over 12,000 F6F Hellcats, and over 15,000 P-47 Thunderbolts, all powered by R-2800 engines. Japan's entire production of the Ki-84 Hayate, its most capable fighter, totaled approximately 3,500 aircraft. The quantitative disparity was matched by qualitative superiority in engines, systems, and manufacturing quality. The surrender came in August 1945. But for Japanese pilots who survived to that moment, the war had effectively ended months earlier. They had recognized the futility of continued resistance not through propaganda or command directives, but through direct experience with technological disparity that could not be overcome through courage or tactical innovation. When Emperor Hirohito's voice crackled over radio broadcasts on August 15th, announcing Japan's acceptance of Allied terms, many aviators felt not shock, but rather confirmation of what they already knew. In the weeks following surrender, American forces began systematic examination of Japanese aircraft and facilities. Technical intelligence teams from the United States Army, Air Forces, and Navy arrived at airfields throughout Japan, documenting equipment, interviewing personnel, and arranging for selected aircraft to be shipped to the United States for detailed evaluation. What they found confirmed the assessments American intelligence had developed during the war, while revealing the full extent of Japan's industrial struggles in the conflict's final year. Lieutenant Yasuhiko Kuroe, the ace who had evaluated captured American aircraft at Fusa, found himself on the other side of the examination process. American intelligence officers interviewed him extensively about his experiences flying both Japanese and American fighters. His testimony provided valuable insights into Japanese perceptions of American aircraft performance and the psychological impact of facing technologically superior opponents. Kuroe described the demoralization that spread through Japanese fighter units as pilots realized they were flying obsolescent aircraft against enemies who possessed decisive advantages. The captured Japanese aircraft that American forces examined told stories of industrial desperation. Late production Ki-84 fighters showed evidence of declining manufacturing quality. Riveting was less precise than in earlier examples. Metal panels showed variations in thickness and quality. Engine components exhibited wear patterns suggesting inadequate lubrication or poor quality materials. These were not design deficiencies, but rather symptoms of an industrial base operating beyond its sustainable capacity with progressively inferior materials. American engineers who tested captured Japanese engines found that under ideal conditions, with high-octane American fuel and careful maintenance, some performed reasonably well. The Ha-45 Homar engine that powered the Ki-84, achieved approximately 687 km per hour in post-war testing with 92-octane aviation gasoline and methanol injection. This was competitive with some American fighters, but these ideal conditions never existed in Japanese service during 1945. The fuel was inferior, maintenance was inadequate, and parts quality was inconsistent. The Corsairs that had terrorized Japanese pilots received their own post-war evaluation. The aircraft that had seemed so dominant in combat were examined not as fearsome opponents but as engineering artifacts. Japanese engineers who examined F4U airframes after surrender focused on manufacturing techniques, material specifications, and system integration. They noted the quality of aluminum alloys, the precision of hydraulic systems, the sophistication of engine controls. Everything confirmed what pilots had experienced. American aircraft were products of an industrial system operating at a different level of capability. For Japanese pilots who survived the war, the transition to peacetime carried psychological burdens unique to their experience. They had fought with dedication and skill in aircraft they initially believed competitive, only to discover through repeated combat that they faced opponents with overwhelming technological advantages. The knowledge that their efforts were essentially futile, that no amount of courage or tactical expertise could overcome the fundamental disparity in aircraft performance, created a particular form of survivor's trauma. Some former pilots struggled to reconcile their wartime experiences with Japan's post-war reconstruction. They had witnessed the destruction of Japanese naval aviation not through lack of courage or poor training, but through industrial and technological inferiority that rendered individual skill increasingly irrelevant. This was a difficult truth to accept. Military culture emphasized spirit, determination, and willingness to sacrifice. The reality that material factors had determined outcomes more than human qualities challenged fundamental assumptions about warfare and national capability. Others channeled their experiences into Japan's post-war industrial development. Former aviation personnel found positions in emerging Japanese industries, bringing lessons learned from defeat. They understood that technological competition required not just good designs but complete industrial systems capable of producing quality products at scale. This knowledge influenced Japan's post-war approach to manufacturing, emphasizing quality control, process refinement, and systematic improvement. The nation that had lost the technological competition in aviation applied those lessons to automobiles, electronics, and other industries. The F4U Corsair itself continued in service well beyond World War II, validating the soundness of its design and the power of its R-2800 engine. During the Korean War, Corsairs flew close air support missions, their ruggedness and heavy armament proving ideal for ground attack roles. The aircraft remained in production until 1952, longer than any other American fighter from World War II. Some foreign air forces operated Corsairs into the 1960s, a testament to the aircraft's fundamental capabilities. The story of Japanese pilots discovering American technological superiority through combat with Corsairs represents more than tactical defeat. It illustrates how industrial capacity and technological development determine outcomes in modern warfare as surely as traditional military virtues. The specific case of engine power disparities between Japanese and American fighters provides a measurable, quantifiable example of how material factors shaped the Pacific War's aerial campaign. Japanese, post-war aviation development reflected lessons learned through defeat. When Japan established the Air Self-Defense Force in 1954, the new service emphasized technological parity with potential adversaries. Japan did not attempt to develop indigenous fighter aircraft immediately, instead licensing American designs and manufacturing them domestically. The F-86 Sabre, powered by a General Electric J-47 turbojet engine, became Japan's first post-war fighter. Japanese industry gained experience manufacturing American engines under license, learning production techniques and quality control methods that had proven decisive during World War II. This pragmatic approach to aviation technology stood in marked contrast to pre-war Japanese attitudes. Before 1941, Japanese naval aviation had emphasized indigenous development, sometimes dismissing foreign aircraft as unsuitable for Japanese conditions or tactics. The wartime experience with American fighters, particularly aircraft like the Corsair that combined multiple technological advantages, demonstrated the cost of technological insularity. Post-war Japanese aviation policy reflected this lesson, balancing indigenous development with licensed production and international cooperation. The industrial lessons proved equally significant. Japanese manufacturing in the post-war era focused obsessively on quality control and process improvement. The Toyota production system, developed in the 1950s and 60s, emphasized elimination of waste, continuous improvement, and respect for workers. These principles reflected lessons learned when Japanese wartime production failed to match American manufacturing quality. The attention to detail in post-war Japanese manufacturing represented, in part, a response to the industrial weaknesses exposed during the war. Former aviation personnel played significant roles in this industrial transformation. Engineers who had struggled to maintain aircraft with inadequate parts and inferior materials understood the importance of supply chain reliability and component quality. Managers who had witnessed production systems collapse under material shortages and workforce disruptions prioritized resilient manufacturing processes. The experience of technological defeat informed post-war Japanese industry in ways that shaped its eventual success in global markets. The specific technical lessons about engine development also influenced post-war Japanese industry. The R-2800's combination of power, reliability, and manufacturability demonstrated what American industry could achieve through sophisticated engineering and systematic production. Japanese engine manufacturers studied American designs extensively, learning not just about technical specifications, but about the industrial processes that enabled reliable mass production. This knowledge informed development of automotive engines, marine diesels, and eventually aerospace power plants that made Japanese industry competitive globally. The psychological legacy proved more complex. Japanese pilots who survived the war carried knowledge that their nation had been decisively defeated, not just militarily but technologically. This created a particular form of national trauma, a recognition that Japan had challenged powers with industrial capabilities it could not match. The response varied. Some former military personnel became pacifists, arguing that Japan should never again engage in military competition with industrial powers. Others became advocates for technological development, insisting that Japan must achieve parity with leading nations to prevent future defeats. The broader significance of the Corsair's impact on Japanese pilots extends beyond individual aircraft performance. It represents a case study in how technological disparities shape military outcomes and influence defeated nations' post-war development. The specific example of engine power, measurable and undeniable, provided concrete evidence of industrial differences that affected every aspect of the aerial war. Japanese pilots could rationalize tactical defeats or attribute losses to specific circumstances. They could not rationalize away the fact that American fighters had engines producing twice the horsepower of their own aircraft. This technological disparity was not hidden or disputed. American aircraft manufacturers published performance specifications. Technical manuals detailed engine capabilities. After surrender, Japanese engineers could examine American aircraft directly and confirm what pilots had experienced in combat. The transparency of technological superiority eliminated the possibility of face-saving alternative explanations. Japan had been defeated, in part, because American industry could build better engines and manufacture them in greater quantities. This was fact, not interpretation. The long-term impact on Japanese industrial policy reflected this brutal education. Japan's post-war economic miracle was built partly on lessons learned from wartime defeat. The emphasis on technological development, manufacturing quality, and industrial efficiency represented a national response to the recognition that technological backwardness meant vulnerability. The pilots who had flown Zeros against Corsairs, who had experienced firsthand the consequences of inferior technology, helped shape a national commitment to achieving and maintaining technological competence. Lieutenant Saburo Sakai survived the war to become one of Japan's most articulate witnesses to the transformation of aerial warfare, from individual skill to industrial competition. In his post-war writings, he returned repeatedly to the theme of technological disparity and its psychological impact on Japanese pilots. "We were not defeated by better pilots," he wrote in his memoirs. "We were defeated by better aircraft, better engines, better resources. The Americans could replace losses. We could not. They flew faster aircraft. We could not catch them when they chose not to fight." This testimony from one of Japan's highest-scoring aces carries particular weight because Sakai was not making excuses. He acknowledged his own considerable skill and that of his fellow Japanese aviators, but he recognized that skill became progressively less relevant as American technological advantages manifested. A highly skilled pilot in an inferior aircraft could occasionally defeat a mediocre pilot in a superior aircraft. But systematic technological advantages, applied across hundreds of aircraft in sustained combat, overwhelmed individual excellence. The morning of April 17, 1944, when Sakai had climbed into his Zero not knowing the true specifications of the Corsairs approaching from Guadalcanal, represented a moment of ignorance that was about to end. Not for him alone, but for Japanese naval aviation as an institution. The combat that followed, and thousands of similar encounters across the Pacific, educated Japanese pilots in the hardest possible manner about the industrial and technological realities of modern warfare. What they learned shaped not just their remaining months or years of life, but influenced an entire nation's post-war trajectory. The knowledge that technological inferiority meant military defeat, that industrial capacity determined outcomes as surely as courage or tactics, became embedded in Japanese strategic thinking. This was the true legacy of the Corsairs' technological superiority, not merely the aircraft destroyed or pilots killed, but the lessons absorbed by survivors and carried into peacetime. The R-2800 engine that powered the Corsair represented more than mechanical engineering. It embodied an entire industrial system, from raw material extraction through precision manufacturing to quality control and logistics. Japanese pilots who faced Corsairs in combat were experiencing American industrial capacity translated into tactical reality. Each encounter provided evidence of capabilities they could see and feel, but their nation could not match. By war's end, this lesson had been learned thoroughly. Japanese survivors understood they had fought against opponents whose industrial advantages proved decisive. The specific example of engine power provided concrete, measurable evidence of this disparity. An R-2800 producing 2,300 horsepower was not merely incrementally better than a Sakai producing 1,130 horsepower. It was fundamentally superior in ways that translated directly into combat advantage. The post-war examination of American aircraft by Japanese engineers confirmed everything pilots had reported. The manufacturing quality, the sophistication of systems, the reliability of components, all demonstrated industrial capabilities Japan had not possessed. This was not a comfortable truth, but it was an educational one. Japan's post-war industrial development reflected these lessons, with emphasis on technological competence, manufacturing excellence, and systematic quality improvement. The men who flew Zeros against Corsairs carried their experiences into post-war Japan, influencing industrial policy, technological development, and national strategy. They had learned through personal experience that modern warfare was decided as much in factories as in combat. That lesson, purchased with thousands of lives and national defeat, shaped a generation's approach to technology and industry. Today, when historians analyze the Pacific Air War, the technological disparities between Japanese and American aircraft stand as key factors in explaining outcomes. The Corsair's dominance was not accidental or mysterious. It resulted from specific engineering decisions, manufacturing capabilities, and industrial organization that gave American pilots advantages Japanese opponents could not overcome. The psychological impact on Japanese pilots who recognized these, Advantages provides a human dimension to statistical analyses of kill ratios and production figures. The story that began with Lieutenant Sakai, not knowing the true specifications of approaching Corsairs, ends with a generation of Japanese pilots, engineers, and industrial planners deeply educated about technological competition. They learned through defeat what victory would have never taught, that industrial capacity and technological development determine national security as surely as military prowess. This knowledge, carried forward into peacetime, helped shape the economic transformation that made post-war Japan an industrial power. The Corsairs that once terrorized Japanese pilots now rest in museums, preserved as examples of American wartime aviation. The R-2800 engines that gave them decisive advantages are studied by engineering students learning about piston engine design. The pilots who flew against them, those who survived, told their stories to ensure future generations understood not just what happened, but why. Their testimony provides a human voice to the statistical reality of technological warfare, ensuring that the lessons they learned through bitter experience are not forgotten. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.